Moving into 6.3, 6.4, this is where we talk about log functions and what their graphs are going to look like. Essentially, the purpose of a logarithm is to be able to approximate things that we don't really know for an exponential. So, this is a really good example here. We know that 10 squared is 100 and 10 cubed is 1,000, but we don't really know the power to get a 500. So we essentially need to do a logarithm. The nice thing about that is logs and exponentials are inverses of each other. So they do have a little special relationship. And so we can kind of convert between the two. Some people like this ABC version. Some people like to see it with XY. So I'm going to go ahead and jot that down as well. But here you can see how these two things are going to move between each other. B is always going to be the base, and you'll notice A and C flip-flop. In the log form, A is with the base, and the exponential form, C is with the base. So let me write down the version for, oops, that I think most people prefer that they're most familiar with. So there's your b to the x equals y, and log base b of y equals x. So again, base of the exponent, base of the log, that always stays the same. Then the x and the y are going to flip-flop. Some people like to just remember that it's going to go to the opposite side. Um, I really don't have a better way of remembering it. I've been trying to think of one and I just don't have one. So that's the best I got, unfortunately. This tends to be the trickiest thing, so that's what we practice quite a bit. We convert and go between the two so you get familiar with it. So let's start with these conversions. I'm going to go ahead and highlight my base so I always remember what it is. And I can go ahead and write log base 5. Okay, so remember now the 2 needs to be on the other side, which means we have log base 5 of 25 equals 2. All we need to do is to convert. Let's do the next one, log base 5. Negative 2 is on the other side, which means 1 over 25 is inside and equals negative 2. Whoop, moving on. Here's my base again. So log base 25. 1/2 is away from the 25, so that means it's going to be of 5 equals 1/2. Log base 5. Again, the 0 needs to be far away. And our last one, log base 5 of 5 equals 1. This is actually a good segue to talking about a quick rule here. If the base and inside of the log match, the answer is 1. Always, every single time. That's a little thing right there worth knowing. Okay. So let's look at these and solve without a calculator. So when they say solve without a calculator, it means that we should really treat this like an exponential. So 2 to some power is going to equal 8. So that means we're looking at 3. That's what we're saying. This is the same thing as saying 3. You're really just rewriting it as an exponential, but it's written as a logarithm. Here, we're basically saying 2 to some power equals 2, right? And I just talked about how if these match, the answer is always going to be 1. So we know that 2 to the power of 1 is always going to be 2. Here, we're saying 2 to some power is going to equal 1. We also know, based on what we've talked about, that anything to the power of 0 will always equal 1. And again, we're writing these things as logarithms, but essentially what we're doing is we're solving exponentials. They just look a little different. Here we have 2 to some power equals 1/8. If you think back to exponentials, This over here could be written as 2 cubed in the denominator, or 2 to the negative 3, which makes y equal the negative 3. Here we have 8, the sum power equals 2. This is saying we need some sort of fraction because we want the number to get smaller. Similar to how 2 cubed was 8, 8 to the power of a third is equal to 2. This is worth noting that this is actually the cube root of 8. This is the power of 1 inside, and the cube root is represented by the denominator, and that is equal to 2. So y is equal to a third. And last one, 2 to the power of y equals 0. There is no solution. It does not exist. It is impossible to get an answer of 0 from an exponential function. It's just not doable. Now, there's two kinds of logs. There's the common log that is written as log. There's also a natural logarithm, which is the inverse of e, which we talked about in exponentials. Most commonly used in a calculator, and the standard is log base 10. If it is base 10, you will not see the 10 right there. It is assumed to be a 10 unless you write otherwise. If it is not a 10, you need to write the number, right? Otherwise, you don't have to. Whereas with natural log, you don't have to write any bases because it's a base of e, and the natural log accounts for that. So we'll use both. I tend to use natural logs as much as I can, but we will see both, and you should feel comfortable using both and make sure you see them both on your calculator. Um, the most common use for this we'll see a lot in science, especially when we talk about decay and magnitude and like pH and stuff like that. That is where these really come in handy. So they are useful, especially if you're in STEM. Sorry, I just heard an ambulance outside and I got distracted. So it is worth taking the time to like feel comfortable. Now, I've already mentioned once that these are inverses of each other, and you might remember a little tidbit about inverses is that the x and y values can switch and the domain and range switch. So that actually makes logs not so bad. Because if you remember, for 2 to the x, we said 0, 1, and 1b were your critical graphing points. Well, now that we have log base 2 of x, we can graph 1, 0 and b 1. Honestly, not that bad, because at this point, we can graph 2 to the x pretty easily. That also means the domain and range are going to switch. So if you remember, the domain was all real numbers and range was 0 to infinity. Well, now those two have flip-flopped. Now the domain is 0 to infinity and the range is all real numbers. And you see that right here, right? Like this function is going down forever and up forever, so that checks out. However, we do have this asymptote that limits our domain. So write that down here. So your domain is going to be 0 to infinity because the asymptote is at x equals 0. The range is all real numbers because it's going up and down forever. Notice also that it doesn't have a y-intercept, right? Again, because it can't cross that axis. So it has an x-intercept, whereas the exponential only has a y-intercept. So again, those flip-flop, and so it doesn't have the other one. Similar to exponentials, I have all of the written definitions and explanations for transformations. I, as usual, like to do the graphs. So let's do it. Again, similar as before, I like to graph the parent function, so I already have that written everywhere in orange, as well as the asymptotes. Now let's talk about the transformations themselves. Here, we're moving up one and down one. We're going to go up and down. Okay, notice that my asymptote is not affected because vertical shifts make no impact, whereas shifting left and shifting right will impact my asymptote. That is an important thing to pay attention to. Let me switch to my dashed line. Oh, that -1 tells you where that asymptote's going to be. +1 tells you where the asymptote's going to be. It is important to graph it on a quiz or an exam because it really cannot touch that curve. So if you're graphing something and it's like this, that is wrong, right? That asymptote is a barrier. Zooming out. I'll do something similar that I did with the other transformations that we had. And we'll do purple for this one, and then we'll do a different color. We'll do like green or something for this one. So here are my x values. I had a 1, a 2, and a 4, and my original y's were 0, 1, and 2. Now for my 3, that's a stretch. So I'm multiplying my y value by 3. So 0 times 3 is still 0. 1 times 3 is 3. 2 times 3 is 6. 1, 0 does not change. My 1 is going to bump up to a 3. And my 4, no, my 2 is going to bump up to a 6. So we are going to elongate quite rapidly. For my 1/3, we are essentially dividing by 3. So 0 over 3, still 0. 1 over 3 is a third. 2 over 3 is 2/3. So the 0 is not affected. We're going to have 2 1/3 and 4 2/3. So this green one is a little too aggressive. There we go. There we go. It's going to compress quite a bit. Scoot back over so you can see the table. So again, the x values have not changed, but the y values have. Last but not least, we have our reflections. Notice that that should have a base of 2. I think I fixed it in your notes at this point, but it should be base 2. This is a reflection over x. So my 1, 0 won't change. And then we'll have 1, 2, and 4, -2. It's just going to face downward. So my y values are negative. Asymptote is not affected. And reflecting over the y. Asymptote is also not affected, but our domain is affected. So the domain is going to be -infinity to 0, whereas on the original, the domain was 0 to infinity. Just a quick little note there. All the other stuff is not affected, like range for that one or domain and range for the for X. Just wanted to make you aware of that. Here are your examples. This is a great time to pause and come back. All right. Let's go through these. Hopefully you tried to do them on your own. We're moving up two. So 1, 2, 1, 2, 1, 2. I realize now I didn't do my asymptote, so let's just draw that one. And little curve. This is going to move left 2. So let's draw my original asymptote really quick, because it is going to shift. There we go. It's going to shift 2 units, so I'll go ahead and draw that. And then 1, 2, 1, 2, 1, 2. Draw that curve. Right, this one has 3 transformations, so reflecting over X, moving to the right, and moving up. So this can be kind of tricky. So I think I'll go ahead and do my negative transformation first. And also draw my asymptote. Doo-doo. All right, reflecting over X, so we're going to be here, here, and here. And then I'll switch to purple. I will do the rest of it. Negative log 2x minus 2 plus 2. That means I'm going to go right and up. So 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. And asymptote is also going to move 2 to the right. Will be here, roughly. Yeah, that looks right. I was second guessing myself for a moment. So our curve should look somewhere like that. I just did this earlier today in class, so I don't know why I'm second guessing myself. All right, moving on. Domain. This comes up in the homework a lot. It's usually also on the final. So logarithms have domain restrictions, just like roots, just like rational functions. The inside of the log must be greater than 0. Actually, I'm just going to write it. Greater than 0. So you're going to solve an inequality. X minus 4 greater than 0, so x has to be greater than 4, which means your domain is 4 to infinity. That's essentially telling you that looks atrocious. This is essentially telling you what the asymptote is. Right? So the asymptote is at 4, which means you're starting at 4 and not including 4 and moving forward. It also means that anything outside of those parentheses is irrelevant. So here we have 3x minus 6 is greater than 0. The 2 doesn't matter. You're just solving the inside because you want to make sure that you know where the asymptote is. So in this case, it's at 2. So your domain is 2 to infinity. Okay, last but not least, the minus 1, irrelevant. X plus 8, greater than 0. X is greater than negative 8. So the domain is negative 8 to infinity. Don't forget, if you are dividing by a negative, the symbol will flip. I realize now that I don't have any examples of that, but something to keep in mind. Let me just think of one really quick. Pressure. Let's do negative 2x minus 4 greater than 0. Negative 2x greater than 4. Dividing by that negative 2 flips the symbol and we get x is less than negative 2, which means negative infinity to negative 2 is going to be your domain. So just a quick note there.